geometric correction, there are a couple different steps that we have to go through. The first thing that we have to do is figure out which geometric model we want to use. So there are lots of different mathematical models that we can use to warp and stretch and twist our imagery. And these options are not all the same. They're not all doing the same thing. And so we want to think about what our terrain looks like, how large a swath our image covers, how much distortion we expect to see in our image, and then we will pick an appropriate geometric model to account for that. We don't want to overcorrect and end up turning our entire image into this complete muckety muck warped twisted thing of silly putty. So we want to use just enough to get our correction done without over warping it. So once we've figured out which geometric model we want, we have to find those ground control points, those tie points that are going to link our pixels in our image to known locations on the ground, either with ground control GPS locations or with another map. So that's the second step, is really going through the process of identifying all of those GCPs, or those ground control points. And then once we have that information, we know what model we want to use, and we've identified all of our ground control points, then we can actually let the software compute this transformation. And that was that first step we were talking about, where we're just going to take the pixels and ignore the data values that are inside of them, but just take those XY coordinates for every single pixel and turn them now into geographic coordinates to make a map. And this will also provide us some error analysis. And this is really important because when we're doing this warping, it's not going to make every GCP line up perfectly with each other. It's going to basically twist and stretch our image until it finds the best fit. Based on that geometric model. But there's still going to be some error. In other words, the ground control point in our image is still going to be a little bit off from the true location that we know with the geographic coordinates. And we can actually calculate that error to come up with some sort of a measure of accuracy of our geocorrection. And then that final step is the resampling. And all that means is it's going to take the actual data that had been stored in each of those pixels, and it's going to figure out which geographic coordinate identified pixel that data should go back into. Because at this point, remember, that grid has been transformed and warped. So it's not like we would just plunk in each pixel value in the exact same number pixel it was in before, because we know that mountainous regions may represent smaller areas on the ground. Maybe a data value from one original pixel goes into that. But in a valley, we knew that it was actually covering a much larger area. So maybe we put the same reflectance information into 2 pixels down there. So in other words, the resampling is really just figuring out how we're going to assign data values to each of these newly warped pixels. We'll walk through each of these steps briefly, and we'll start with the different types of geometric models. So when you are opening up your geocorrection tool, one of the first things it's going to ask you is to identify which geometric model you want. And as you can see, there are lots of different options here. And essentially, what these different models are doing is determining how you can take your original image. Let's assume it's a piece of paper, right? It's two-dimensional, a number of rows, a number of columns. Imagine that's a piece of paper lying on the table. Different models will allow you to stretch that piece of paper in different ways. As if, okay, instead of a piece of paper, imagine it's a rubber sheet, because we can't really stretch a piece of paper. So this rubber sheet, depending on the model, is going to be stretched in different ways. One of the most common geometric models is called a polynomial warp. So when we're doing this, when we're stretching our rubber sheet, we're essentially warping the image. And what these polynomial models are essentially just equations. They're algebraic equations that determine how distances between pixels should be changed as you move across an image. And these polynomial transformations not only correct linear distortions in an image, like in other words, it could just twist it all, shift it over a order of magnitude, but it also can correct nonlinear distortions. So there are different orders of polynomials that you can use. Just like if you had one order polynomial, it would essentially draw you a line. If you have a second order polynomial, right, allowing it to have two different coefficients, now you could have more extreme warping to your image. So the higher the order of your polynomial, the more warping you can accomplish as it twists and pulls and stretches your different your imagery. So let me give you a visual because I think that's hard just to think about in terms of words. If we're talking about just a first order polynomial, so say I selected a polynomial model. This first order is also referred to as an affine warping. All that it's going to do is shift the origin of our image. So maybe this was the original. It will basically plop it down in the right spot on the earth so it can just not any twisting or warping, it can just literally move it around. It can also rescale the image, so it will give us the appropriate sort of bounding box on the ground for this image, and it also allows us to turn or rotate the image. But that's all that the first order polynomial can do. It cannot do any actual stretching or warping of the image. So this would really only be appropriate in incredibly flat areas for small image swaths, right, where you're not worried about the curvature of the earth. If we increase that to a second order polynomial, it can still do all of that. It can shift where the image lies, it can rescale the image, it can rotate the image. But now, in addition, it can actually stretch across the pixels if it needs to account for the differential size on the ground that each of our different detectors is recording from. So this does allow us to correct for the curvature of the Earth, or those camera lens distortions, or those off nadir angles. So this is really useful for air photographs, which has that roll, pitch, and yaw. This allows us to take care of that. Or for those larger satellite images, which have more curvature to the Earth as one of those distortions. And because there may not be that much variability across an image, this is also appropriate for small geographic areas. So that would be the second order. But as you can imagine, once we move up to the third order polynomial, now we can really start adjusting and twisting things, not only in two dimensions in terms of, stretching or pulling our rubber sheet in two dimensions. Now we're actually allowed to twist or raise or lower that sheet as well in order to match the locations on the ground. So this is really good for imagery that is highly distorted, or if we know we're dealing with a pointed off nadir imagery. The thing to be aware of, though, is that sometimes if you don't need it, if you don't have this much distortion in your image, this can actually result in sort of a false sense of quality to your geocorrection, because the more you warp, the more likely you are to have your GCPs, those ground control points, line up. And so with each order of polynomial that you go up, you're essentially forcing that fit a little bit better, but it doesn't mean that it's correct across the entire image. In fact, it may be overfitting one of your control points. In other words, it may be twisting or stretching too much just to force two of those GCPs to line up, where it actually ends up messing up all of the pixels in between. So we do have to be careful once we get into these higher order polynomials. Each of those polynomial models we just discussed essentially are creating a fit for the entire image. So it looks at all of the GCPs across the entire image and creates a geometric model to fit the whole thing. But there's also piecewise models where instead of looking for that global fit, it's actually going to segment the image into these smaller triangles, and then it's going to fit each of those individually. And what's nice about this approach is that it essentially is only going to warp or correct segments of the imagery that need it, that are distorted, rather than sort of stretching and warping an entire image. So this is really useful when you perhaps have distortions only in certain locations within the image. Maybe the topography was only really variable in one part of the image, but was relatively flat everywhere else. Or imagine that one of the flight lines was relatively smooth and turbulence only picked up on this aircraft later in the flight path. So this is really a much more refined geometric correction. It also takes a whole lot more time. And so it can be something that you don't necessarily want to use unless you have to. The other nice thing about this, though, is that if you do happen to have GCPs that are, you know, perhaps incorrect, it's really only going to affect a small portion of your image as opposed to one bad GCP that maybe you thought you had it in the right spot but you didn't. It's not going to end up sort of distorting in a bad way or making more incorrect the entire image. So those are probably the most common geometric models. There are others, but they're rarely used in our field in natural resources. So we'll move on to that second part, which is once we have our model identified, now we have to identify those ground control points so that we can link our image to a known coordinate location. Now, more recently, there have been some automated GCP creation tools that have been incorporated into our software, but really even those automated processes are just to essentially throw some points on the ground where the software thinks it's finding similar patterns in the reflectance, but it still needs to be verified manually. So this really is often a manual correction. You have to make sure that you go into your image and you can clearly identify that intersection or that object that you're training on, and then it matches your known location on the ground. In lab, we're going to be practicing this geo-registration. Remember, registration is when we're using an image with known coordinates as a reference so that we can apply and assign coordinates to our image. And sometimes this is really pretty straightforward, particularly if the two images are in the same spatial scale, so that when you look at a location, they're going to look very similar. But it can also be very hard because sometimes you might be using a reference image that has a completely different resolution than the one you're looking at. And so you now have to think about the broader patterns across the landscape and hope that you're matching up in the right location. And since we're going to be practicing this in lab, and also because this is just a really good skill to have, because it's often it's a common assignment that remote sensing analysts have to work on, I want to give you some guidelines for how to select these ground control points. And some of these guidelines are really obvious. Clearly, you have to be able to identify whatever location you're using in both images. So it has to be distinct and you can identify that correctly in both your image and your reference map. You also need to be able to precisely locate them. So for example, I may be able to identify a lake in both my image and the reference map, but I have to know precisely where in that lake I can match those two files up, those two images up. And so it needs to be something that has some sort of a very small scale heterogeneity so that you're really able to see, oh, I'm not just at the intersection of these two roads, but I'm clicking on the southwest corner edge of pavement of those two roads. And obviously if you have coarser resolution imagery, you won't be able to be that refined, but you still want to be able to think, well, where in this pixel? Is it the center of the pixels that line up, or is it the edges of the pixels line up? So you really do want to try to locate precisely in each image where those ground control points should be located. The other thing that's maybe not as clear is you really want to pick points that are not subject to change, and that's because often we will be using a reference map from a different date than what our imagery is. I mean, and often it's older. The most common reference images that we use are aerial photographs, and those are typically 5 to 10 years older than the image that you're using, and so you have to make sure that you haven't, for example, picked a stream, for example, that maybe experienced flooding, and so the channel path has been modified slightly, or the edge of a forest that maybe could have been harvested or cut, or the edge of a field. You know, maybe it might be really obvious where a farmer plowed in one image, but it may not have been plowed in a different year. So make sure that you're identifying things that are not likely to have changed. The other piece to keep in mind, especially if you're using, well, I guess actually if you're using either the polynomial or the affine, the piecewise affine models, is that you need to have those ground control points spread throughout your entire image. You cannot warp an image just based on a bunch of points that are clustered in the middle or clustered in the bottom. The whole image is going to be warped, and to make sure that you're not over warping, You have to make sure you have those tie points in the corners, along the edges, as well as distributed throughout the image. And then each model also gives you a minimum number of ground control points that it wants in order to mathematically come up with the warping algorithm for your image. And usually that's at least 30 to 50 ground control points per image. And that really also depends on how much distortion you have in your image. Obviously, the more distortion, the more ground control points you're going to want in there, and maybe even clustered together around those distortion areas, so that you can be sure that you're warping without overwarping. So just to give you an idea of what the minimum number of GCPs might be for each different model, we can look at this table, and you can see that as your polynomial order increases, so do the minimum number of GCPs. So for example, if you're doing a polynomial order 3, you are going to need at least 10 GCPs before the software is even going to compute any kind of model or offer you any kind of accuracy statistics. But really, it's recommended that you try to be 2 to 3 times more than that minimum at least. So that's not just the recommended number of GCPs, that's a recommended minimum. Right, and I actually usually like to go even higher than that. Let's put it this way: you can't have too many ground control points unless they're wrong. So you don't want to guess. If you're not absolutely sure about where you're placing a ground control point, then don't place it. But if you have a lot of really easily identifiable targets across your whole image, there's really no reason why you wouldn't include those, and you would just stop at 30 GCPs if it was pretty easy to just plop down a couple more. And I will go through this process of collecting GCPs in a separate video, which might help you get started on the lab, so be looking for that as well. So once you've got all of your GCPs selected, before you actually run the transformation, that's the next step. The next step is to actually have the software run the transformation and warp the image. But you want to make sure you're looking at your statistics from just those ground control points based on the model you've selected, so that you can make sure that what you have is pretty good. And so what we use to assess the accuracy is a root mean square error, and that's reported to us in the ground control collection tool. We can see each GCP that we lay down. We can see its X address, its Y address, that's in the original image, and then we can see its reference geolocation, that would be in the reference image. And what we're getting over here, these residuals are telling us, well, how much is it off in the X direction if we were to apply this geometric model. So this software is basically trying to tell you, as you add GCP points, how far off your ties, those two ties, would be to each other if the model were run. And so we can see how far off we'd be in the X, in other words, sort of east to west or left to right direction, and how far we are off in the Y, or the north-south, up-down direction. And then these two residual errors are combined to give us a root mean square error. And what this root mean square error is calculating is it's saying, what is the average distance between the input GCP that we have for our image and the reference image GCP. So as we're warping, they're not going to line up exactly for every single GCP. This root mean square error is telling us the distance between the two, right? And it's important to keep in mind that the units of this root mean square error and our residual errors are in the same units as our reference image, right? So if we have our reference or our map that we're using to correct our image, and that's in meters, well, then this is telling us how many meters we are off in the X direction and how many meters we are off in the Y direction. And our goal, really, what would be a good or an accurate geocorrection would be if your root mean square error is below 1 pixel. So in other words, if you can say on average we are off by less than 1 pixel. Right? So if I was doing Landsat imagery and I had 30 meter pixels, right, that would mean that I would be shooting for an overall root mean square error. So not just the root mean square error for every single GCP, although that would be nice, but an overall error that is below 30 meters. And it's nice to have the root mean square error for each individual GCP, because what this means is once we've established all of our GCPs, we can go back and actually sort on this and identify those that are off the most and double check them and make sure that they're accurate. And if they're not, we can slide them around or move them slightly. Um, and we can do that, or we could eliminate them if we just can't seem to get those 2 points to line up. Maybe we're wrong and we're not identifying the same spot in both images. So we can basically clean up our overall GCP network by looking at these individual root mean square errors. But the total root mean square error is up here, and that's essentially the average of all of these. And this is the value that we want to be less than whatever our pixel size is, so that we can say that we have basically overlain these two images so that they are less than 1 pixel off of each other. And one of the implications of this is that we really can't say that, oh, you always want to have an accuracy, a root mean square error less than 1, or a root mean square error less than 10. It really depends on the spatial resolution of your imagery, right? Because if you're looking at a Landsat image with a 30-meter pixel resolution, if you're off by 1 meter, well, that would be just about nearly impossible to do, because now you're talking about knowing exactly, if you divided this pixel up into 30 different mini pixels and 30 different mini pixels that way, that you were selecting the exact right spot inside of this pixel. For your GCP, but we just can't expect the same spatial accuracy from these coarser resolution sensors. Whereas if we're getting down to some really high resolution sensors, then I would expect absolutely we should be able to have a root mean square error down around 0.5 if we were talking about meters as our units of measurement there. But the other thing I want you to keep in mind, one of those other guidelines is, especially when you're dealing with this coarser resolution imagery, sometimes it's really hard. Like, even though I can say, oh, I want to find the junction where this bridge crosses this water body, but the reality is that, that's a really big pixel right there. Where within that junction am I going to select? And so sometimes you might actually find yourself looking for patterns across pixels in order to identify where within a given pixel you should place your GCP. And if you're not sure, you can just shoot for the center, the centralmost point for that object that you're trying to identify. But it can get pretty tricky. It's definitely another art form. One other thing to keep in mind that's a common misperception is that root mean square error, and you should report your root mean square error so people know how accurate your geocorrection is, but that root mean square error that comes out of this warping transformation process is really only telling you how well on average the warp fits the GCPs that you've selected. Right? So you may actually pick a different set of GCPs and have that root mean square error change. And so while this is nice to help us refine our warping and try and get it as good as possible, it's not truly an independent test of how accurate the registration is. To do that, we would have to identify an independent set of ground control points and see how well we match up our pixel locations to those known geolocations. And this becomes increasingly important when we're talking about those higher order polynomials, because the higher the order of the polynomial, the better the fit you're going to get, just because the math becomes more complex, not because you're actually warping it the way that it needs to be correctly warped. So sometimes you may see a really good root mean square error that does not necessarily mean that your entire image has been warped accurately. So these are just little things to keep in mind. Okay, everybody, hang in there. We're up to the last step in the geometric correction. So we had our original input image. We added some GCPs and selected a model, which allowed us to transform our original grid into now a new grid that has geometric coordinates associated with it. But now we have to do the resampling. And the resampling is when we take this empty grid with geographic coordinates, and we're now going to determine which pixel values, which DN values, should go into each one of these pixels. This is essentially how we populate the grid with the reflectance or with the DN data that the sensor collected. Again, I think it's useful to have a visual to understand why we have to do this or how we do it. So imagine that we had our original file here, and imagine it's just binary with zeros and ones. So we have our zeros and we have ones. That would be the white and the green. And this is what the file actually looks like. It's just that nice square, given number of columns, a given number of rows. And each of these black corners, imagine this is one of our GCPs. This is an identifiable object in both our image and the map we're referencing to that we can identify. So we use these GCPs, and the GCPs linked to the reference map are telling us that actually we need to rotate that image so that it's lying over the correct area on the ground. So this is really where those corner pixels should be located. And so then we can use our model, right, to figure out if we need more warping. If we're just a polynomial 1 warping, all we're doing is sort of rotating it, maybe resizing it or shifting it left and right. Okay, but we now have this new grid, and notice that the new grid doesn't line up with the original grid, right? So we had to resize it. Imagine we had to resize it with our polynomial warp. So now each pixel in the new transformed or warped grid is a different size than the original pixels in the image, right? And also sometimes they overlap two different of the original pixels, right? So in other words, it's not that easy. It's not like it's a one-to-one correction where all that we did is just shift this over one pixel to the right or one pixel down. We've completely warped and rotated and resized these so that each of our new pixels in the grid with the geometric coordinates is now located over some different combination of pixels from the original image. So we have to figure out which values we're going to put from this original image into this new transformed grid, and that's the resampling. And we have different resampling methods that we can choose from, but essentially we're trying to figure out, well, do I call this new pixel, do I call that a 0 or a 1? And sometimes you end up seeing something that turns out like this. This was the best approximation that you could get as to which values to apply to your new grid based on the old image values. I gotta say, this is actually pretty bad. Usually we can do much better than that, especially if we have higher spatial resolution imagery. And just like we have different geometric models for that transformation step, we also have different resampling algorithms that we can choose to use. And we're going to go over each of these so you can understand how they're different. But essentially the most common are the nearest neighbor resampling, bilinear interpolation, or cubic convolution. Nearest neighbor is the simplest. It literally takes the center location of each pixel and it just looks back to the original image and it pulls out whichever DN value is closest. So even though you may have overlap or there may be 2 pixels in your new grid that are associated with 1 pixel in your old grid, they would both get the same value. It's literally just saying I'm going to take whichever DN value from my original image is most closely linked to this new transform warped image when I do that transformation and overlay it on the original image. What's nice about this approach is that you're really maintaining and preserving the original DN values from your imagery, right? We're not making any changes to the values. We're just deciding where the values from the original image are going to go in the new grid. And because it's this simple, it's really a nice approach when you don't have a lot of particular computing capabilities, like not a lot of processing speed. It runs a lot faster, let's put it that way. And also, you would have to use something like this if you have categorical data as your DN value. So if, for example, I was trying to take a land cover classification that had no geometric coordinates associated with it, and I wanted to overlay that with a map and apply some projection information to that, I can't do an average of a categorical variable. I would have to just basically pick whichever pixel from my image and whatever class that was assigned, I'd have to choose that for my new grid data value. But the disadvantages are that it really does make a more sort of blocky transform. And so you end up not seeing those nice smooth lines that you had in the original image, especially if those are linear objects. Also, because you're just grabbing the nearest pixel, which may not actually be representative of the same surface area on the ground that was covered, you can be off. The error can be higher, so it's not going to be as accurate as some of the other models we have. And in fact, what ends up happening is if you're always just grabbing the nearest pixel, there are some of the original pixels that will never be the nearest pixel to the new output grid, and so you may end up losing some pixels entirely, the data that was contained in those pixels entirely. If we move up one level in complexity, the bilinear interpolation now actually takes a weighted average of the 4 pixels from the original image that are nearest to our new grid pixel center. So in other words, if my ground control point was right here in both images, I would basically say, okay, well, what are the 4 pixels nearest that ground control point? And it would just average those 4 DN values and then report that into the 1 pixel of our new resampled output image. So obviously there are some advantages and disadvantages to this approach as well. It's definitely going to be more visually appealing. We're going to have a smoother transition across pixels. We're not going to see those sort of unnatural breaks between pixels. And it doesn't take too long to run, right? We can run bilinear interpolation without overwhelming our processing capabilities. But the other thing to keep in mind is that it is actually changing those DN values, right? It's now a weighted average. It's not giving us the original data that the sensor corrected or that it collected. And so in a sense, you're almost smoothing over your entire image, meaning that any extreme values, maybe there was one pixel that really had extreme absorbance or extreme reflectance, it's going to be washed out because you no longer see those extreme values. You only see the average of the 4 values that surround each of your GCP points. And it also ends up smoothing out your radiometric resolution. Just because you're losing those extreme values, it means the total range, possible range for all of your DN values is much smaller, and so you don't have as much distinction between pixels, right? So you end up basically washing out a lot of your data. Cubic convolution tries to take the best of both the nearest neighbor and the bilinear interpolation, incorporating that into its approach. And essentially what it's doing, again, we have our tie points that tell us, which pixel in our new output grid matches the original image. And what cubic convolution is going to do is it's going to give that nearest pixel a really high weighting in an average across a larger area. So even though it's averaging across now a 4 by 4 grid, which should theoretically smooth out that image even more, that was one of the disadvantages of bilinear interpolation, but it's okay because it's actually weighting that central pixel, that nearest neighbor, much higher in that average. And then if you look at the next nearest pixel, that's weighted a little bit less. The next nearest pixel is weighted even less than that. And so by the time you get out into that 4th pixel, it's really not having that much influence on the original DN value in there. So essentially what this is doing is it's trying to give you a nearest neighbor approximation, but remove that sort of blocky and chunky appearance that you might get with nearest neighbor by taking the weighted average across that larger grid. So this really is the method, the resampling tool of choice for most people when they are doing a geometric correction. It makes a very smooth, visually appealing image, but it still retains that radiometric range so that we can still have power to distinguish between different surface features. But there are some disadvantages, and one of the worst is that we do end up losing some of our spatial resolution because we're essentially averaging over this larger area. So it's taking away a little bit of that heterogeneity that we would expect to see across a landscape, and then it does slightly reduce that range that we're seeing in our DN values. It makes the contrast a little bit lower. Not as much as the bilinear interpolation, but it does impact that. But I think maybe the biggest disadvantage of this, if I had to think of one, is that it takes longer to process. This is an awful lot of weighted averages that are being calculated. If you think about how many hundreds of thousands or even millions of pixels are in a given image, and to have to do this weighted average across every single one of those can take quite a long time to run. So that would be another example of bring additional homework to work on while you're running this resampling step. Also, just being honest, I do typically end up using the nearest neighbor resampling method only because I'm typically working with hyperspectral data. And my hyperspectral data, I really care about the values for each of those spectra. I really care about each individual band's reflectance value because I'm trying to relate them to very specific absorbance features. And if you start, instead of just actually giving me the spectra as exactly as it was collected from the sensor, if instead you start giving me some average of spectra across a larger area, you may be washing out my absorbance feature entirely and I'll no longer be able to detect it. But that's again how, as a remote sensing analyst, you have to make decisions which aren't necessarily right or wrong, but which do have to be justified. And so my justification would be that I really want to maintain the integrity of that raw spectra that the sensor collected so that I can most closely link that to my known absorbance features. I just want to give you an example of what that means. So here we have a geometric correction that was conducted using the nearest neighbor resampling, and here's the exact same GCP points, right? So we're using the same transformation matrix. It's just how we then refill those DN values, and this one is with the cubic convolution. And so what I'm saying is that I'm willing to sacrifice having this pretty smooth transition across my image and have this more blocky appearance because it retains for me the original DN values. So notice how much sharper the contrast is between this water and this, I guess it's some sort of a byway, a bridge or a byway. And so it would be easier for me to distinguish that if I have this nearest neighbor, whereas they look more similar in this image here with the cubic convolution. So these are trade-offs that you have to weigh, and what's most important, again, to the objectives of your analysis. If I had to summarize, I would say that the bilinear interpolation or the cubic convolution, which is the most common approach, are fine whenever you're just trying to create some visual. You just want to have a nice map that looks pretty, and you're just going to accept the fact that they're altering the DN values. But this is not okay if you really are interested in the spectral information that are contained in each pixel. And also, it's not possible to do the bilinear interpolation or the cubic convolution when you have categorical data, right? You just can't average forest, 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 or if it's forest, land, forest, land. It's impossible to do this mathematical weighted average if you have class data. You can conduct a geometric correction in almost any remote sensing or GIS software, but I happen to like the Imagine interface. But both Imagine and Envy have the same functionality in terms of warping the image and resampling. It's just a question of how the actual tie points are gathered and how you can visualize the fit. So we'll practice that a little bit more in lab this week.